We have the big pleasure today to have Mircea Dinkę from Princeton University together with us. Mircea studied chemistry, inorganic chemistry at UC Berkeley, if I'm correct. He moved afterwards for his postdoctoral stay to MIT, where he joined also the faculty over the years. He recently, in 2024, if I'm not mistaken, he became now professor directly in Princeton. He holds the Alexander Stewart Professorship for Chemistry. He received numerous awards, among the Blavatnik National Award, ACOS Award, the Alan Waterman Award, and he does beautiful work really related to challenges that tackle us all for storage and consumption of energy, global environmental concerns. And yeah, using materials, in particular MOFs and also COFs, to address these really challenges. And today, it's our big pleasure to have him here to talk about water-stable MOFs, water management, maybe, we don't know. We are very looking forward to a talk for building water-stable metal organic frameworks for buildings. And yes, with that, I thank you very, very much for coming, and the floor is yours.
All right. If you can hear me well, just thumbs up,
Wonderful.
please. Great. Okay. So yeah, pleasure to, well, be here. I'm at home, but be there virtually with all of you. Um, and yeah, to share some of our work, my group's work in making water-stable MOFs. I think I see lots of friends logging in, even unexpected ones. So it's really nice to be here. Okay, since this is a an audience that by and large knows what MOFs are, I don't have to introduce them, but I will go straight into why we're interested in making them water stable, and not just fundamentally why that's important, but also because water stability in MOFs can lead to applications in a wide variety of fields, starting from water capture, atmospheric water capture. We'll see that that could become important in the future. Air conditioning, I'll spend probably a few slides at the end telling you about a company that we started that works in this field, desiccants, desalination, and so on. Now, what is particular about water when it comes to adsorption into microporous materials, as I'm sure many of you know, is that it actually has a very unusual isotherm. I'll come back to it a little bit in more detail, but by and large, when you adsorb water into a material, when you look at the quantity of water adsorbed on the y-axis here versus, let me just change the pointer to a laser pointer here. Um, as a function of, say, relative humidity, or you can think of that as relative water pressure, you'll find that it has this sort of sigmoidal shape where there's a little bit of water, if any, adsorbed at low relative humidity, so during dry spells, you will. And then there's a huge uptake, usually under a very narrow relative humidity range, and then you get saturation, basically the maximum capacity. Okay, so the question is, okay, one, how do you make these materials water stable? But then also, how do you understand and control this sort of sigmoidal shape? Um, as we all know, moths are wonderful. They can save the world in many different ways. But what makes them water unstable? Okay, and of course, that has to do with how the ligands, the organic parts, these typically aromatic ligands, and the inorganic building blocks, typically metal clusters, and most typically second row transition metals, right, are connected to each other. And uh, I think we would all agree that most MOFs are made from carboxylates. Of course, there are many other types of ligands, acylates, pyridyls, and so on. But basically, you're setting up a bond between a metal, a second row transition metal, and a carboxylic acid. That bond, even though we draw it nicely as nice little lines and such that looks covalent, of course, those bonds are ionic. And so what that means is that most moths are salts, and salts are soluble in water. Most salts are soluble in water. So it's that nature of that metal ligand bond that causes the problems with water stability. if you can make that bond stronger, or as we'll see, if you can make it kinetically more stable, at least you can hope to have um, water-stable MOFs. Okay, so the other thing that I think maybe fewer people even in the field appreciate is that if you take any MOF, and in fact any porous material, it will always be unstable relative to some dense phase. This is true for zeolites, this is true for mesoporous carbons, this is true for mesoporous silica. Basically, any porous material is thermodynamically uphill relative to some dense phase. Now, it's also true that we don't always know what that dense phase is. For zeolites, we know it's silica. It's basically quartz. Quartz is the thermodynamically stable form of silicon dioxide, but zeolites are by and large silicon dioxide as well. So for MOFs, we know that most of them probably will collapse under pressure. So that dense phase, whatever the shape of that dense phase is the thermodynamic phase of these MOFs. So we have to just live and accept with the fact that all MOFs are unstable, okay? Or that all MOFs are metastable. Um, However, so is diamond. Diamond is metastable, okay, and relative to graphite. But none of us think of it as being unstable. And so, of course, what that means is that it's kinetically stable, right? Like if it's really, really metastable, that means that there's a huge activation barrier from going to this higher energy phase to the dense phase. And so, in essence, what we want to do when we want to make water stable MOFs is we want to make them as kinetically stable as possible, because we're never going to have them thermodynamically stable relative to some dense phase. So what can we do? Well, everybody's favorite water-stable MOF, not mine, is this series of zirconium carboxylates. Okay, they're actually wonderful materials, to be fair. And what happens there is people assume that it's the strength of the zirconium-oxygen bond. And it's true by and large, but you can think of that concept from the perspective of this kinetic stability. So if you think of most, say, second row transition metal carboxylate MOFs as living in this purple potential energy surface, what you'll find is that, okay, if you take a zinc carboxylate, it'll have a weak bond. That's a weak bond. That means that both the porous phase and the dense phase of that zinc oxygen or zinc carboxylate MOF will live higher in energy than a corresponding zirconium carboxylate MOF. And if you think both of those, or if you can imagine that both of those zinc and zirconium carboxylate MOFs will have the same structure, even though I understand that's not necessarily true, and the same transition state, that basically means that the activation energy for destroying the zirconium MOF is higher than the activation energy of the zinc MOF. And so this is not entirely the correct way to think about this, but that's one way to realize how a thermodynamically stronger bond will lead to more stable MOFs in general. So in some cases, these zirconium oxygen or zirconium carboxylate MOFs can live up to about 350, maybe 400 C, which I would take also as the absolute maximum that any MOF can probably live at, because eventually, to call something a MOF, it has to have an organic part, and the organic part itself will start pyrolyzing above, 350 or 400 C, because benzene itself is not a thermodynamically favorite form of carbon. Um, Okay, a different way and perhaps more intuitive. And by the way, actually, once if you accept that you want to that you can make stable MOFs by increasing the strength of the metal ligand bond, uh, you can switch the metal from zinc to zirconium, but you can also switch the ligand. So instead of taking a strong acid or relatively strong acid like a carboxylate and replacing it with, say, a tetrazole that has the same pKa, you can actually replace it with a much weaker acid like a triazole or a pyrazole. And because these are now, 10 orders of magnitude weaker acids, that means that the conjugate base, which is what you would use normally to make them off, the perazolate, the triazolate, will be much stronger itself, and therefore the metal ligand bond will be stronger. And indeed, um, actually, as a graduate student, I worked with peracelates, and you can make MOFs that are stable up to about 400 C if you start using these peracelates. And this is important because I'll come back to them. A different way to think about kinetic stability, and perhaps a more intuitive way, if you want to think about concepts of lability, for instance, of the metal-ligand bond, is to really consider the metal kinetics itself. And this is probably one of my favorite reactions of all time, but it's a little bit counterintuitive because it's a reaction where nothing happens. And so basically what you do is you say, okay, what if I have some metal salt in water? Metal surrounded by six water molecules in the coordination sphere, and you put it in water, and you ask, how fast does a water that doesn't sit on the metal, is just in liquid water, free water, exchange with a water that does sit on the metal? So thermodynamically, nothing happens. Delta H for this reaction is zero. So by definition, nothing happens. But of course, that process does happen. And so you're asking, how fast does it happen? And you can measure these rates. And what you find is that transition metals will sit in an enormously large range of rates. So from something that we call really labile, like copper 2 plus, chromium 2 plus, will exchange with 10 to the ninth per second. And so that's basically diffusion limited, right? So it's extremely fast rates. Whereas if you look at something like nickel, okay, if you think of platinum, maybe that's intuitive, but even nickel 2 plus has an exchange rate of 10 to the fourth, copper 10 to the ninth. So one way to think about this is that, let's say I make an identical, structurally identical MOF, one with copper 2 plus and one with nickel 2 plus, let's say terephthalic acid. If I find that my copper MOF is stable for 1 day, which we wouldn't take to be very stable, this would automatically mean that the nickel MOF is stable for 100,000 days, which is longer than my lifetime for sure. Um, so this is really, I think, illuminating because it's telling you that, now you can make that sort of argument for 1 hour versus 100,000 hours, right? For whatever you want. And so this is simply exchanging copper for nickel. And in fact, this is one of the reasons, if you do, this is just an empirical thing I did a while back, there aren't that many nickel MOFs. And the reason for that, I think, is because nickel exchanges very slowly with ligands, and therefore it's hard to crystallize nickel MOFs. Um, so, it's entirely based on essentially freshman chemistry arguments of this kinetic lability. How does this translate to a MOF? Well, water is not that different of a ligand in terms of ligand field from a carboxylate. And so if you think of metal carboxylates, if your activation energy is high for that ligand exchange, basically exchanging ligand for water, thereby hydrolyzing the MOF, if you have something inert like nickel or vanadium or gallium or iron or aluminum, you'll make something much more inert. Aluminum MOFs, again, you can spend, I think, hours on this graph and just kind of like educate yourself. But aluminum MOFs, people make it or take them to be stable because aluminum is very oxophilic. But what you realize is that aluminum is actually also very inert when it comes to ligand exchange. And so that's why, again, it's partly why it's so difficult to make aluminum-based MOFs. Or chromium-3 MOFs, usually you need to make, you need to reduce it to some extent and so on and so forth. Okay, so you can make water-stable MOFs. You can make them extremely water-stable but they're all going to be kinetically stable. Um, so I'll give you some examples of how we use that, but we can get into applications as well. So one of the first things that, and many people work on, I think, in our field, starting with Omar Yagi, really, is this idea of getting water from the atmosphere. And for me, this actually started with a very sort of unusual circumstance in that, when you fly as much as I do, you sometimes pick up these magazines that an airline offers you, and you really have nothing better to do. You read that magazine. In this case, it happened that that magazine had an issue on water. And so I was reading this actually. This should have been maybe 15 years ago or so. So this graph is 15 years old. This is literally from that magazine. And it basically showed something that really resonated with me. Uh, and maybe this is small for some of you to read, but these bar graphs in the lower left are saying that the world population between 2005 and 2030 will go from about 6.5 billion to over 8 billion. Now, the black part of that bar is the proportion of people living under severe water stress. And in this article, this is not just some metaphor, it has a very specific meaning. Severe water stress, it means that you don't have access to fresh water on a daily basis. And so in the Western world, this is inconceivable, turning your tap and staying for a whole day without fresh water. But by 2030, or even today, there's maybe a third of the world population that doesn't have access to fresh water on a daily basis. And by 2030, half of the world population won't have access to fresh water on a daily basis, much of it driven by climate change. Um, Now, okay, that's bad enough. This is the really scary part next to it. This shortfall, it says that by 2030, about 2 billion people will not have access to water, period. Even if we could move around the water that we do have on the planet, we just won't have enough water to go around for everybody to live the same standard of living that the Western world does. And so that's really scary. It makes you wonder, okay, where is the water? I mean, the planet is full of water, right? And so this is all the water. This big blue square is the oceans. 97% of our planet's water is in the ocean. 3% is fresh water, okay, which is the one that we can use. Of course, we can do desalination, but that has a huge cost, and most countries can't actually afford to do desalination. And then it has environmental problems as well. So 3% is fresh water, but two-thirds of that fresh water is actually in ice caps and glaciers in places like Greenland and Antarctica. And so we're melting those, but that's not good because we're putting them in the ocean. Um, but basically, the usable fresh water is almost essentially all groundwater. So it's all in the ground, and we're depleting those reservoirs at a really, really fast rate. Everything else, like rivers and lakes, is tiny. It's only 0.3% of all the water on the planet. Um, Okay, where else do we have water? Turns out there's a lot of water in the atmosphere. I think you could guess where I'm going with this. How much of it? Well, it turns out that 0.04% of all fresh water lives in the atmosphere because air is humid. Um, so we can do a calculation. It's a little bit silly, really, but you can say, okay, if everybody lived like Americans, God forbid, okay, or maybe Germans. I don't know. Maybe they use a little less water, but Americans use on average 100 gallons per day. You got to clean yourself twice a day. You got to clean your dog. You got to wet your grass and so on. So we take that and say 8 billion people want to use 100 gallons per day. So that's about 400 liters, right? You need 2.7 cubic kilometers of water per day for the entire planet. Doesn't sound like much, actually, but you could get that, all of it, from the atmosphere. Of course, you'd be like, okay, well, that means we have to circulate the entire atmosphere. And if any of you are engineers out there, you'll see that that's basically impossible. But the idea, of course, the more realistic scenario is to make up some of this expected shortfall with water from the atmosphere. So this is the promise, right, that some people who work in this field, right, will say, okay, this is what we want to do. Then you actually have to hit reality and say, okay, where's the market? Where is this shortfall of water? I mean, I live in the northeast of the United States. It's wet year round. Like we are not lacking fresh water. There's humidity everywhere, right? And so what you'll find is that the usual suspects are Southern Europe, Spain, Italy, Greece, Bulgaria, and so on. The Middle East, big trouble, of course, is very dry. And India. India is in big, big trouble with fresh water because most of their fresh water for farming comes from aquifers, and they're being depleted at a much faster rate than they're being renewed. But then you say, okay, great, absorbing fresh water from the atmosphere doesn't have to involve a MOF. You can also do it with a very old technique called dewing. This is basically collecting dew in the morning or by just putting some fabric that collects water when it's really, really moist outside. So you can see that most of the world could actually do dewing instead of just adsorption through some fancy sponges. Membranes are also doable in really dry places like the Sahara. But then where the sorbent idea could be useful does overlap to some extent, let's say with the southwestern United States, with much of the Middle East actually, but not with India. Okay, India is wet enough to do dewing if they really wanted to get water from the atmosphere. So there is some overlap with those dry areas. Okay, so this is where the MOFs could come in and say, okay, let's make a MOF that is water stable, that will work under the conditions that it needs to work in order to absorb water directly from the atmosphere. So what do you actually need to do? Well, you basically need to play off of the difference in humidity between night and day. So at night, even the driest places on the planet, like the Sahara, the Atacama deserts, will have humidity that is maybe 10 to 15%, maybe even 20% higher at night than during the day. So this is where a water harvester, for instance, would want to live. You want to be on this line, the sigmoidal shape on the blue one, so basically have a material that will spontaneously absorb water at about 20% relative humidity, and then spontaneously release water when the humidity decreases below 20% because it just doesn't want to take up water. But what if you want to make a desiccant? Well, for a desiccant, you want it to absorb water at very low relative humidity because it needs to basically be a desiccant to dry your air. If you want to use MOFs for humidity control, you want to live between 45% and 65% humidity, right? So now you have this problem that if you're a material chemist, you say, okay, well, how do I make a material that will actually allow me to play around this humidity range and deliver whatever application wants? Um, so for this 10 to 30%, you can go ahead and try to make some materials and hope to get lucky. Okay. And this is what my former student Adam did, for instance, with one of these triazole ligands. And what he found is that if he takes this triazole, which remember it has a pKa of about 9, 10, so a much stronger base than a tetrazole or carboxylic acid, and he reacts it with nickel chloride. Nickel, again, is one of those metals that is very inert, so it'll make very water-stable MOFs. You can make a MOF that looks like this. I think this is familiar now. It actually has the same topology as MOF 74. And this now will absorb water exactly at around 30% humidity spontaneously. Okay, it'll saturate at about zero point 0.9 grams of water per gram of material. This, by the way, as you'll see, is actually quite a high saturation. And then, so it'll basically absorb its weight in water and then release it at about 45 degrees with very little hysteresis. And you can do this in many cycles. And of course, if you want to make a device out of this, you will want to make hundreds, if not thousands, of cycles, depending on how many times you want to cycle this. Uh, but what we learned too is that there's probably a so-called critical diameter that allows you to absorb water and desorb it without much hysteresis if you prevent the water from liquefying inside of the MOF. So you can imagine that when this water goes inside of a MOF, um, it is neither in the gas phase nor in the liquid phase. It is in the so-called adsorbed phase. This is a phase that is denser than water vapor, but not quite as dense as liquid itself. And so that's a good thing because if it starts liquefying, then you're changing the phase of water to liquid water, and there's going to be a heat capacity associated with changing it back to the vapor phase. So that's an energy penalty that you would pay in order to release the water and collect the water after you put it in your sorbent. Um, so if you compare this with other MOFs, again, this is fairly old. We have much more recent comparisons now. But at the time, this yellow part of the overall water uptake was the exact water content that you would take between 10 and 30% in that relevant region. So this was at the time better than essentially all other materials out there, including zeolites or carbons. Um, and you can do sort of back of the envelope calculations to even price the cost of water delivered by this. What we also learned at about the same time is that if you start making these calculations and costs and everything, cost of the material, you'll find that for now, delivering water directly from the atmosphere is still not very competitive relative to other methods of producing and transporting and delivering fresh water. But the same materials or any material that would absorb water spontaneously at a given humidity could be used for things like humidity control and air conditioning. And if you really want to have your material applied and if you want to have an impact in the real world, you'll start looking and really learning about where this is a problem. And again, the sort of usual suspects are the hot and humid areas, like the middle of the planet, Mexico, Brazil, India, Indonesia. Of course, everybody in the United States, whether it's hot or not, has an AC in their home. So that means that your market penetration, if you want to make a new AC, is very low. You're not going to replace those ACs. People already have them. You might be able to convince Europeans to buy some ACs the hotter it gets. Even in places like England, we've learned about heat waves and such. China has a standard of living that is very high. So many of the Chinese households, it gets very hot in China, but they already have ACs. So basically, what you want to do is to penetrate the market in these areas, India, Indonesia, Brazil, Mexico, where people are just buying new ACs. Why is this important? It's not just important to make money. It's actually important because once somebody in India buys an AC, they will keep it. It's a huge investment for them, even if it's like $150, maybe $200. And those ACs are rated to work for maybe 15 years or so. So once they've invested into an AC, they will not buy an AC for another 15 years. That means that they will buy these horribly inefficient ACs that we have today, and they will consume energy, even though you might be able to make a much more energy efficient AC. So this has a huge impact on the planet, on the environmental control. This is a picture from a New York Times article showing, really the magnitude of the problem in India. You can see these little, really crappy ACs, right, that are springing up on like just random buildings in India, right? This is one picture only. And you can imagine how inefficient this is, right? In general, HVAC systems consume about 13% of all energy on the planet. And so this is going to be a huge problem moving forward. So again, you go back to this idea, where do you want to be on this graph? Well, you want to be in this region now where you have a material that works between 45% and 65%. So again, go back to the drawing board, and this becomes frustrating very quickly because now you're sitting there and just making MOFs and hoping that one of them will be working in this region. Because again, what defines the position of this sigmoidal shape along the relative humidity scale is how hydrophilic or hydrophobic your material is. And so you can kind of understand this if you imagine sort of the entrance of a pore. This is meant, this sort of funnel is supposed to be the entrance to one of these tiny little pores, right? So imagine this width here is about 1 nanometer. And your water molecule is smaller than 1 nanometer, but not much smaller. and it sees a hydrophilic entrance. That means it loves the pore surface. And so it'll start attaching to the surface and it'll easily go inside of your pore. That means that a material that is hydrophilic will absorb water, will let water get in, even at very low relative humidity. But if you have something hydrophobic, the water molecules come in, they see something that is not pleasant to them, and they'll start accumulating at the entrance of the pore before they go into inside of the hydrophilic pore. In other words, you have to apply more water pressure to force the water molecules to go into the hydrophobic pore, which is why you need to go to higher relative humidity, higher relative pressure of water to absorb any water inside of the pore. Once they go in, they'll have made essentially a hydrophilic surface with themselves inside the pore. So this is kind of like they help each other get into the pore once they go over a certain threshold. So it's a simplistic way to think about this, but again, you want to make materials that will allow you to engineer them to work at a certain relative humidity. So if you take these points, for instance, okay, where is the top of the sigmoidal sort of strong uptake here for these different kinds of materials? So you can start plotting them as just points taken as explained previously. So this is where it becomes much more, I think, quantitative to think about MOFs in this way. And Jules is a former graduate student. He still works in our lab as a group manager now. And so he really taught us a lot about how to think about MOFs and water stability from, I think, very simple, otherwise thermodynamic arguments. Um, so there is a thing called the Kelvin equation. Basically, describes the condensation of water in pores. This goes back to what I was telling you about preventing the water from actually becoming liquid inside of a pore. And the Kelvin equation basically says that if you have a capillary, it will have a characteristic surface tension that will be defined by the radius, volume, and so on. And this surface tension will define at what relative humidity you will start seeing capillary condensation. Now you can think of these tiny little pores in MOFs as being governed, at least to some extent, by the same theory of capillary condensation because they're just tiny little capillaries. And so what Jules did is to basically replace the um, this surface tension parameter with the enthalpy of water absorption, or basically it's the difference in enthalpy between liquid water and the energy of interaction of one water molecule with the pore. And then you have the same things otherwise. You have the pore size and the area of a certain water molecule as determined by its kinetic diameter. And so you rewrite this Kelvin equation, and then you also define the adsorption quantity of water in terms of certain constants and the pore radius. And these constants will combine everything from topology to density to volume occupied by the framework. Okay, so these constants are just framework specific. And then what you can do is you can substitute this R into the modified Kelvin equation, and you can predict basically how this quantity of water will evolve as you change certain parameters, as you change the radius of the framework, the hydrophilicity of the framework, basically delta G. And so you can plot these now in along, or if you plot this, you'll get certain curves. We call this, or Jules called them, isoreticular curves. And this, I think, is very powerful because it allows you to tell a lot about what you can, and I think even more importantly, what you can't expect from designing a new material. So for instance, if you decide to say, okay, well, I can apply reticular chemistry, increase the radius or the size of a ligand, and that will give me more water. Yes, you will get, like, if you increase the size of the ligand, you will increase the size of the pore if you maintain the same topology. But you'll see that you'll also actually move along the relative humidity scale. So you won't stay vertical. You'll actually go to the right if you increase the size of the ligand, or you'll go to the left if you decrease the size of the ligand. Okay, so you can't purely go vertical if you maintain the topology the same. This is intuitive. If you have delta G, basically the hydrophilicity increasing, you can move to the left. If you have the hydrophobicity increasing, you can move to the right. So again, you can spend a lot looking at these curves and learning what you can and cannot do by designing a new material. And even I think empirically more illuminating for me at least, it was that if you start plotting essentially all the MOFs that have been measured to our knowledge along these, where the S shape occurs, you'll find that it's fairly common to have um, MOFs that absorb a lot of water at large relative humidity. Okay, so you even have points like this, so even 2 grams of water per gram of material. And there's quite a few MOFs that can absorb at very low relative humidity, meaning they're very hydrophilic. But there's this sort of empirical line or quadrant where nothing exists. And that's not saying that they can't exist. It's just that as far as we can tell, nobody's been able to make a material that is both very hydrophilic and absorbs a lot of water. So that's now a design question. Can we actually make such MOFs? And I think it's a very interesting question, right? And it's something that maybe can move the field forward, right? If you're interested in water absorption. And you can read all about this in a very recent communication that Jules put together. So how do we go about making such materials that can now allow us to move along the relative humidity range? Well, having learned what we all just learned from these more quantitative treatments of water absorption, and also with an eye towards application, real world application, you want to also think about the cost of the ligand. And so I've already shown you one of those bis triazole ligands. Those were actually popularized by Dirk Volkmer in Germany. Um, but you can make the same clusters, the so-called Kuratowski clusters, with a much cheaper ligand, and that is made from benzidine. This bis diamine of benzene or biphenyl is cheap because it's a component in membrane and plastics. So you can just turn it directly in one step into the triazole, and then when you make a MOF, it has actually this very interesting sort of chiral structure. But the point is that it's much easier to produce than the so-called MFU4L. And when you now look at this MOF, you initially make it with zinc. But my group and others have shown that this can be exchanged with many other metals, including and then the anion that provides charge balance can also be changed from acetate to chloride. And so if you then simply play with the composition by changing the metal and the terminal anion, you'll find that you can move from say 100% nickel to 100% zinc, and you can access all these different compositions, and they're basically all the same structures, all the same surface area if you do nitrogen adsorption isotherms, but they allow you to move along the relative humidity range by 40%, right? So you can move from a material that would be good for, say, water harvesting from the atmosphere to a material that would be much better for dehumidification and air conditioning, for instance. Without otherwise changing the maximum capacity, because again, you're using the same exact material. And we've done a lot of much more fundamental studies to show why this is happening. And basically, it has to do with, as one might expect, with when the water clusters versus when it doesn't. And you can follow this very nicely by IR. You can also measure the vaporization or the enthalpy of adsorption of water in these materials. And what you'll find is that there is a region at very low relative humidity of water or very low water uptake where the enthalpy of water interaction with the MOF essentially is much higher than the enthalpy of vaporization. That's basically saying that water loves the MOF more than it loves itself. Okay. And that's what doesn't allow it to liquefy, which is a good thing again. So what can you do with this? Well, you have a material that absorbs water. It really loves to absorb water in the right humidity range. That means that you can take the water out of the air, then cool the air, and then put it back in the air. Why is this useful? Well, if you think about air conditioning, um, you'll realize that a lot of these air conditioners have to work, well, all of them have to work with the air that is given to them. And often, especially in places like New Jersey or Mexico or the tropical world, it is full of water, right? The relative humidity in the summer often in New Jersey is 90 to 100%. So that means that you have to cool this humid air. Water has a huge heat capacity. So when you're cooling the humid air, you're putting a lot of energy in cooling the water in the air. And that's just terrible because you don't need to cool the water in the air. You just want to cool the air, right? So by taking the water out, then cooling the air, and then putting just as much as you want. By the way, you don't want when you do air conditioning now, you get this cool and humid air. So it's kind of like a wet shower if you're going into one of these really humid areas. So by taking the water out and then humidifying it just at the right percentage, you have a much more comfortable environment. And so that's exactly what this startup company is doing. It's basically taking MOFs, coating them onto surfaces, um, and inside of an air conditioner, and then dehumidifying it, and then cooling the air. And that gives us about 40% energy reduction or um, energy reduction in the consumption. So these are now humongous appliances that go on top of buildings. You can see this is one of those giant trucks. And so this is just one AC. This will supply an entire building or warehouse. And this has MOF in it. And I think that's the cool part, right? Like, and now we're seeing a lot of real applications of MOFs. This thing has several kilograms of MOFs inside of it. Okay. And it's the secret juice that makes it work. Um, it's basically a plug and play device. It gives us 40% lower electricity consumption, and payback period is also much shorter because of it. Okay. So I think I'm on time to let us have some questions, but I do want to thank my group. I always end with these slides. They're a fantastic group of people. I travel a lot, not today, but I do travel a lot, and they're incredibly self-sufficient and independent. And hopefully next time I'll have the time to chance to tell you more about what they do on other fronts. But with that, thank you again for having me, and I'm happy to answer some questions.
Wonderful talk. Thank you so much, dear Mircea. I'm pretty sure we have plenty questions, and I would be happy to have the first questions. Don't be shy.
Evelyn, can I start?
Yes,
I
please.
didn't figure out how to raise the hand because I'm just clapping. I know other people clapping. So I have actually two questions. Mircea, what is the currently known most water-stable MOF, and what would be theoretically the most water-stable MOF in terms of metal and linker?
I mean, I think you have to define the parameters of what it means to be most water stable, right? Like if you say, okay, most stable in a round room temperature, right?
Hmm.
Um, say from -20 to plus 45 or whatever. Um, I would say that some of these nickel pyrazole MOFs, as well as the chromium
Yeah,
MOFs,
the chromium
are
for me is
really,
chromium
really
always.
stable,
Yeah, nickel
right?
poverty.
Um, that's just my hunch. Again, I think you really want to do some aging studies. You
Hmm.
know, I think many people do realize this, but steam is one of the most corrosive things out there, right? So I think
Hmm.
making stable water stable to steam, right, for which there would be good applications, is also very challenging. Um, but you really have to define the parameters.
I see. And I was also interesting. I didn't know that so less nickel MOF are known. I didn't look in the literature deeply, and it is so hard to do them, yes? Or nobody tried hard enough. Did you try it?
It's something, I think obviously you'll find nickel-based MOFs.
Yes.
But for a long time, I started in this field when people still had trouble making MOF 5. I was, as many people, I was trying to make anything with BDC, right? And when you try to make nickel BDC, it's actually really hard to crystallize anything. And
Mm.
for a long time, even today, I'm not sure that a pure nickel BDC phase exists. Maybe there is some, but for a long time, the structure of just nickel BDC was not known.
Mhm. Okay.
Okay. Other questions?
Can you hear me?
Yes, Jonathan?
Yeah.
Okay.
Okay.
Okay,
I'm
now
sorry, I
it's
didn't have also a camera, so I just provided right now.
very good.
I'm kind of in another field involved. I mainly work with CUF, but on batteries. And well, one simple question is, you talk about in the last slide about kilograms of MOF into it, but
Yeah.
what about the scale up? Because in the case of CUF, it's quite tough. So my question is how tough it is with MOF, because tunability is quite common, but then how it is easy accessible to get a lot of powder, let's say. That's the
So,
issue.
obviously we work with tens of kilograms of MOF. There are many companies out there that make hundreds of kilograms of MOFs, right? Not all MOFs can be scaled up. I will say that, right? Like, it turns out that ligand is usually the expensive part, and the solvent is the expensive part, right? Because in the lab, we make very dilute solutions. We start with very dilute solutions, often containing DMF. DMF is a huge problem for industrial scale up, right? But evidently there are, I would say, probably tens of MOFs out there at least that could be scaled up in the tens of kilograms. And if you find the right application, I think many more could be scaled up, right? But it's a catch-22 for many of these companies, right? Um, to decide to scale up something before they know they have a customer, or once they have a customer, like investing a lot of money to scale up a particular MOF. So it is a problem, but I think it's a problem that many fields have, and I think it's also a problem that is way overblown. It's a problem that's really becoming solved or can be solved if you find the right application.
Mhm.
Thanks.
The questions?
Yeah, I have one question. Hi.
Hi, Kwejo.
Hi.
It's a really nice talk. So yeah, I have a question. How the solvent playing a role to making a water stable MOF? Like, is there any role? I saw that if you make MOF in water or mixture of water DMF, in some cases we find that it is stable in water. Even some MOF which is we make in water, but it is not stable in water. So is there any role? Is there any relation with that? You have, yeah, how we can.
I mean, something I always tell my students, and again, I think maybe, people internalize it, but don't really realize it fully, is that any MOF is unstable or is soluble in the solvent mixture that you make it in.
Mhm.
It has to be true because otherwise you wouldn't be able to make it, right? The way you grow crystals is ligands attach and detach until they actually make the right structure. The fact that they detach, that means that the MOF is at least soluble to some extent in the ligand, in the solvent mixture that you make it in. So when you make a MOF in water, it has to be soluble in water. The question is again, how fast does it dissolve in water?
Mm.
Right? How kinetically stable is it in the solvent that you make it in? The more kinetically stable it is, the harder it'll be to crystallize because it'll take more time, right?
I would
So I
have
don't think it matters which solvent you make it in. It matters how fast does it dissolve in the solvent that you're interested in.
Okay. To add on this question, one more question I have. So if I say some MOF is stable in water, so how to define it? It should be stable in water for 24 hours. It should be stable in boiling water. Or are there another definition for that? Like generally when
Again,
I
you have to decide your application. If you're
so
going to make an air conditioning unit that you're going to put on a huge building and somebody's going to pay $200,000 for it, well, they're going to expect that to be stable for 2 to 5 years or whatever you promise, right? If you're going to make a MOF that has to be stable for half a day because that's how long the catalyst will have to be stable for your industrial process, then it's half a day,
okay,
right?
got it. Thanks. Thanks.
Yeah.
Yeah.
Thank you. Thank you very much for a very nice talk. Actually, you partly already answered my question. So about the stability of the MOFs which you use in this AC for buildings, for how many years do you expect that they are stable? And do you think about reusage of the, even when they are not stable, even when they are destroyed by their function, is there, do you plan to reassemble them from the same building units on which they basically decompose, or it's like on the it's easier to use new resynthesize new MOFs, in your opinion?
This gets a little bit into sort of like the internal workings of that particular startup company, but basically what we're gearing up to do with Transera is to have sort of cassettes that can be exchanged maybe every 2 years or so, and there'll be modular such that you don't have to disassemble the unit and then you just kind of like exchange the sorbent. It's kind of like a filter if you want to think of it that way. But we think that this will work for tens of thousands of cycles.
Thanks.
maybe just briefly link to that. It goes actually also in the same direction. I originally wanted to ask from the thermodynamical perspective, because you show these graphs more for the metal sides, and of course what's happening if I have a modulator and other gas molecules in, but also now if you're moving forwards now in the direction of sustainability, is there any, how should I phrase it? Is there any theory behind where you can predict which MOFs could be actually done in water or in other solvents which are more sustainable, for example, than DMF or others? So it's all very, very linked and similar in the question.
Yeah, I mean it's a great question. I think maybe this is where some of this data mining and this is all going to be, my guess is it's all going to be based on empirical data mining and predictions. But that's not really something we've looked into.
Fair enough. Aisha? You have a question?
I'm just a warning. I will have to go in 2 minutes.
Okay, so a very brief question, Afaf.
Actually, it's going to be a fast question. Thank you for the nice talk. Actually, just regarding the MOFs that are using for indoor humidity control that now you are applying for buildings. So how do you really control the desorption part, just to have it at 45% and not going like lower than this?
So first you have to pick the material that will work in the range that you want. And I think that some of that prediction is basically what Jules's work I mentioned. And then second, how you engineer your actual device has to do a lot with like the flow of air, how fast you flow air through it, at what temperature, all of that will really depend on the engineering part.
Actually, my question, when the material is saturated, so from the engineer point of view, how do you activate the desorption?
Yeah, just flow of air.
Okay. All right. With that, I don't know if Wojciech has a very, very brief question, 10 seconds.
Yes, I have a very brief question. Hello, Mircea.
Hi.
Thank you for this very inspiring talk. So my question is, what is the challenge in water absorption now? Am I correct that what you said, we are looking now for the hydrophilic MOF with the highest capacity, water capacity, or do you see in other direction?
I mean, on a fundamental, I am interested in populating that upper left quadrant. Okay, but I don't think that's the only question, right? I think there's still interesting questions on like the microscopic interaction of MOFs with water. Different MOFs will actually behave in different ways. I think there's interest in understanding transport of water, right? Like how fast does the water adsorption and desorption occur, and what dictates that? And on the more applied side, of course, is how do you lay down these MOFs onto surfaces? How do you make that coating stable? That's super important, right?
Absolutely.
Yeah.
Absolutely.
Okay, I do have to go.
Wow.
Thank you very much.
Many
So I
thanks for,
appreciate everyone.
yeah, really, thank you very much for being with us. And then
Yes.
we will record this and we will have it online soon. Thank you very
Okay.
much. See you for next
Thank
time.
you much.